Amines are based on ammonia with one or more of the hydrogens substituted for a carbon chain. They can be classified into primary, secondary and tertiary in exactly the same way as you classified alcohols. If you have a primary amine, then just one of the hydrogens has been substituted for a carbon chain. In a secondary amine, two of them will have been substituted, and in a tertiary amine, all three will have been substituted for carbon groups. You need to be able to name amines. There are two ways amines are usually named, and that's either using amine at the end of the name. So if I had a structure that looked like this, I would call that methyl amine. Or if you end up with two functional groups, then you can use the prefix amino. So for instance, if I had a group that had a carboxylic acid and an amine, then this would be 2-amino ethanoic acid. So the carboxylic acid has taken priority at the end of the name, so we've used the prefix for the amine group. Have a go at naming the following formulae. So have a go at naming these, pause the video, write them on a piece of paper, then press play once you've got the structures. So these are the answers that you should have got. We've got methylamine, which was used as an example on the first page. We've then got phenylamine. Notice the benzene ring there. Diethylamine. We've got two separate ethyl groups, so the prefix di is used. And then we've got the amine group. And this one, we have a benzene group, then we've got a methyl group, so we call that phenyl for the benzene ring, methyl amine. There are two ways that amines can be made. One of them is an AS mechanism that you should recognise. So we start with a haloalkane and we react it with ammonia. It's a nucleophilic substitution mechanism. You need to be confident in drawing that mechanism. So we start with a haloalkane, react it with ammonia, and we get our amine. Problem with this method is it doesn't stop there. The amine that we've made is just as good a nucleophile as the ammonia we started with, so there's nothing to stop this then reacting with more of the original haloalkane, and in that way we get secondary amines, tertiary amines, and eventually quaternary ammonium salts. There is another way of making amines, and that's by the reduction of nitriles with a nickel catalyst. So you're reacting them with hydrogen, you've got a nickel catalyst to speed it up, and we're going to get the amine. This tends to be the favoured method because it's only making one product. If we use the reaction of haloalkanes and ammonia, we're going to get a mixture of products. We can separate them fairly easily by something like fractional distillation, but if you're trying to make one amine, then it's not going to be a good method to use. So this would be the preferred method. If we want to make aromatic amines, they tend to be prepared from nitrobenzene. So we can start with nitrobenzene. We would react it with hydrogen, usually using something like a nickel catalyst, or we can be more specific in our reducing agents and we can use a tin or an iron catalyst and concentrated hydrochloric acid. So we're just putting the hydrogen in brackets because it's coming from an acid, or it could come from hydrogen, and that's going to give us our benzene ring with our reduced group to make the amine. If we look at the properties of amines, it's all down to the fact that they've got this lone pair of electrons on the nitrogen. That means they can work in several roles. They can work as a base, and they can neutralise acids. They can work as nucleophiles, because they've got a lone pair that they can donate to something that's electron deficient. And they can behave as something called a ligand. Now, ligands we'll come across later on in the course. They are basically a substance that forms a coordinate bond with a central metal ion. And because nitrogen has the lone pair of electrons, it can donate those to form a coordinate bond. As I say, we will cover those later on. So if we have a look at the basic properties first, nitrogen with a lone pair of electrons can form a coordinate bond with a H+ ion. So if it can mop up H+ ions, then it's neutralising them, so it's behaving as a base. And here we've got an example of ethylamine reacting with an H+ ion to form the ethyl ammonium ion. There'll normally be a negative ion associated with the acid, and that can very often join on to make a salt. One of the definitions of an acid is a proton donor. So its consequence base would be a proton acceptor. And we say that amines are Bronsted-Lowry bases. Bronsted-Lowry is one type of defining an acid and a base. When they're put into water, they form a weak alkali. It's a weak alkali because it's a reversible reaction. The equilibrium will lie quite a long way to the left. But as we've got a few hydroxide ions in there, obviously the concentration of hydrogen ions would go down. We've got a few hydroxide ions in there, it's going to be an alkali. How strong a base it is depends on the amino group, and that depends on the lone pair. Anything that increases the electron density or the availability of this lone pair is going to make it a stronger base. Anything that pulls that lone pair away into the carbon chain is going to mean it's a weaker base, because it's less likely to be able to donate those electrons. Have a look at the following. I would suggest you draw them out and think about whether the lone pair of electrons is going to be pulled into the structure, or whether the rest of the molecule is going to donate electrons to make the lone pair more available. The more available the lone pair, the stronger the base. Try and put the following into order of increasing basicity. Again, pause the video, put them into order, and then press play once you're ready. So you can see the most basic one would be ethylamine. We've got the carbon chain, which is a very good electron donator. Methylamine, slightly shorter carbon chain, so less electron donating. Phenyl methylamine is next. Notice there's a methyl group between the phenyl and the amine. Then we've got ammonia, and then we've got phenylamine being the least basic, and we'll have a look at why on the next slide. So the weakest bases are these aromatic or aryl amines. The reason these are so poor at being a base compared to the others is because we've got the benzene ring, and the benzene ring is an area of delocalized electrons. If you have a nitrogen directly bonded to the benzene ring, then what is going to happen, that the nitrogen, the lone pair in the nitrogen, is going to end up going into the delocalized ring and becoming delocalized, which means it's less available. If it's less available, it's going to be a weak base. With ammonia, we've only got 3 hydrogens around it. Hydrogen only has 1 electron, so they're not going to be particularly good at donating electrons. So this lone pair will be reasonably available, but there's nothing to add to it. If we start swapping the hydrogens for carbon chains, carbon is going to be far more electron donating. If it's electron donating, it's going to make the lone pair of nitrogen far more available. If it's more available, it's going to be a stronger base. So the aliphatic amines are going to be the strongest bases. The nucleophilic properties of amines, this is all revision from AS. If you're not confident drawing these mechanisms, or if your mechanisms are a bit ropey, this is something you need to go over and revise. You need to be able to draw a mechanism to show how ammonia will react with any haloalkane. Be very careful when drawing your mechanism. Sometimes it helps to put the partial charges in. That will remind you where you're starting. Make sure the curly arrows either start on a lone pair of electrons or on a bond. Don't ever start them from random atoms. Again, remember, ammonia is neutral when it starts. It is donating its pair of electrons, which is effectively giving one up, so it's going to end up with a positive charge. That positive charge is neutralised by the electrons in the bond with hydrogen being donated to the nitrogen, leaving an H+. That is helped along by another ammonia molecule. This bit is never normally given a mark. It's worth putting in, just remember that this is the product. You very often lose a mark if you put HBr at the end, because that's not what's formed. You're going to get ammonium bromide salt as well. You've then got to be able to carry that mechanism on and show how that the amine that's formed is going to behave as a nucleophile, because it's still got a lone pair of electrons on the nitrogen. There's nothing to stop that reacting with the original haloalkane and forming your secondary amine, and so on. Here's the structure of a quaternary ammonium salt. Don't forget to put the negative ion that's going to be associated with it. The nitrogen is always going to have a positive charge because it's got 4 bonds. So you're going to have the negative ion, and that's why it's a salt. We can't go any further removing any more hydrogens because there's none left, and nitrogen no longer has a lone pair, so it's not going to behave as a nucleophile. The quaternary ammonium salts, once they're formed, are cation. Remember, cation is positive ion, surfactants. They're used in fabric conditioners and hair products. They reduce static by coating the surface of the cloth or hair with charge, so it reduces the static properties. You now need to make sure you're happy with these mechanisms. You also need to have a look at the notes on amines and acyl chlorides and acid anhydrides. You need to be confident in writing mechanisms to show how amines and acyl chlorides react together.